It's feeling a lot like 7 and not 6. Daylight savings is awesome in the morning, but not at night. Oh well. Oh well. We'll get used to it. We'll get used to it. I did want to point something out. Hey. Oh, I put it to the side. I was like, I gotta know who's teaching that. Whoever it is.
2 people.
Yeah. So I initially had not included section 7.4, but then I looked at the final exam that we have to do and decided we should probably do 7.4 because there are 2 questions on there from 7.4. So I made some adjustments, should be fine. But I did update, so if you're following along in the notes that I have, I did update them just today, okay, to include 7.4, so this is where I'll be working off of. Okay. So, oh man, it's a lot of admin today. So there are some sections that I will be cutting for sure. 7.6 and 7.7 we won't be doing. Okay. And so we'll do all the way up to 7.5. And then we have our test. But before I forget, I'm gonna have to do the video thing on Wednesday next week. And I apologize, but I hope that that's okay because we don't see each other on the Monday. And then I'll post a video for Wednesday, okay? And so unless you prefer, so there's an appointment and I can make it, but I can't make it back for class. And so I could do it just live on Zoom if you'd like, or if you want a video that you can watch anytime. Doesn't matter to me, kind of the same amount of effort on my part. And so we'll see. I'm not catching any vibes. So I'll stick to my video because then I can post it before the weekend and you can just watch it whenever you want. Okay. Depends on how far we get in this week to cover the rest of chapter 7. Yeah. And so, but that's on Wednesday next week. And then of course, no classes on Monday, the 10th, because November 11th is on a Tuesday. And so we get a mini little break. That's nice. And then test 2. So after the week after next, we'll have test 2 review, bless you, and then test 2 on the Wednesday. And so we'll do the same thing. I'll post a practice test. I encourage you to try it in advance, and then we'll go through it together in class on the Monday before, and then we have test 2 on November 19th. Now, it's on chapters 6 and 7, but of course, only the sections that we're covering, 7.1 to 7.5. So we wrapped up financial math last week, and today we start a new chapter on sets and counting. Counting sounds ridiculous, right? But counting is good. Counting 1, 2, 3, 4, 5. I mean, in theory, that's kind of what it is. But what we mean by counting is if you have 4 shirts and 2 pairs of pants and 3 pairs of shoes, then how many outfits can you make, right? That's counting as well, right? And so learning tools for counting things like that, okay? But today we'll start with sets, okay? And buckle up because there's a lot of terminology in this first section that I need you to have a good handle on. And then we'll be able to kind of use that terminology. But of course, I have to introduce it first. So, introduction to sets. Oh, any questions before I start? No, yes.
When will the practice questions be up for the midterm? I know it's not a while, but
they should be. So this one, I'm not changing very much in terms of content, except sneaking in the 7.4, so I'll have to adjust it a little bit. But next week, late next week, Thursday, Friday, probably.
Okay.
See what I can cook up.
Okay.
Good. I'll try to keep it in mind. Try. So, sets. Sets are usually a collection of objects. And its members are called elements of a set. We use set notation, which looks like this. So here, this is what we call set notation. So we use these curly brackets, where we use capital letters usually to denote the name of a set. And so here, so we name the set by using capital letters, like capital C, for example. And we enclose its members, so the elements, in braces. And so these are the elements of a set. Trying to color code these. So we can have maybe members of a chess club: Ken, Bob, Tran, Shanti, and Eric, right? And we have 1, 2, 3, 4, 5 elements in this set. And so here, there are five elements in the set C. It's possible to have an empty set. And so a set with no members, or no elements, I should say, although they say members, I guess, we use members and elements interchangeably. And so elements or members, I'll do that. So if there are no elements, we call it the empty set. It's a special set. And so the empty set is denoted by this symbol. I haven't seen anyone writing their zeros like this. Usually I make a little note if I do see it, because it is really common that you write zeros like this just to indicate that it's a zero. But now that we've introduced the empty set is not zero. And so the empty set looks like this. And it is a set with nothing in it. It's in the name, right? But also note that the empty set is not zero. Because zero is one element, which isn't empty, just has no value. So, like I said, lots of terminology. So far, we've talked about a set, the elements of a set, the empty set. Two sets are equal if they have the same elements. And in a set, the order of the elements does not matter. Does not matter. So if you have Ken, Bob, Transhanti, and Eric, that's the same set as Bob, Transhanti, Eric, Ken, and so on and so forth. Okay, so they're equal if they have the same elements. I think if I asked you, hey, are these two sets equal to each other? Then you would be able to answer that without memorizing that term, right? Another one that I think is fairly intuitive because we use the term subset kind of maybe not every day, but we've heard it before, probably. So A is a subset of a set B if every member of A is also a member of B. Now, visually, what that can look like is if you have B represented by a big circle, right? With all the elements in B are just in this circle. And then if A is a subset, then A is going to be some group inside of B. We write I guess I have it here. Let me just highlight it instead to keep it nice and simple. So just because there's a lot of text here, if the set C is Al, Bob, Chris, David, and Ed, so A, B, C, D, E, right? Simpler. And A is Bob and David, then A, Bob and David, right, is a subset of C. We usually write it as A is contained in C. So how you read this is, so you read this as A is contained in C, or A is a subset of C. Is fine too. You can get particular. This A is a subset of C and is allowed to also be C, right? Because it's got the equal to down here, but we're not going to worry about that. So for us, it's just going to denote the subset. But like I said, right, A here is allowed to be equal to C. Okay. Every set is a subset of itself. Okay. So you're allowed to take all of C as a subset. It's just not very interesting, but it's allowed. Okay. And the empty set is a subset of every set. Okay. Which is just saying, hey, you're allowed to choose 0 of those elements. Okay. So I'm going to highlight this. Not an example in sight. We'll run through all this terminology and then we've got examples. If A and B are two sets, and usually we use A and B just kind of to denote any set, any general set, then the union of A and B, which is written as A, and then it looks like a capital U, you can read it as union, or if you want, you can read it as or. Huh? So A or B. So the union of two sets is going to be the set of all elements that are either in A or in B or in both A and B. Huh? Now, eventually, what we'll introduce is called a Venn diagram. Huh? But I think we might be, let's introduce it here. Copy. Just going to do some adjusting here. Wait, hey, I don't want this. That's old. There. So what's called a Venn diagram looks like this. Or I'll introduce it first. Venn diagrams are used to visualize sets. I actually already did it without calling it a Venn diagram. This is technically a Venn diagram, right? Where I have a circle for B and a circle for A, and I show that A is inside of B, right? And so this is how I visualize sets. We start with a box on the outside. And if I have a set A, and in general a set B, they're allowed to overlap. The overlap are all those elements that are in both the sets. And so what this is going to look like, let me see if I can grab a highlighter, then the union of A and B is going to be everything in A or in B or in both A and B, which means it does include that overlap. So A or B looks like this. Nice. A lot of people get confused by the overlap, right? But just remember, it's allowed. So it can be in just A, it can be in just B, or also in the overlap. Okay? Let's see if I can. I'll do this. So I'll do a Venn diagram for the next one as well. Oh, and there's a typo in here. It's not so much a typo, but it's, well, it is. It's a typesetting error in LaTeX. So we talked about the union of two sets, which I usually read as or, right? And so you can read this as A or B, which means that we're also going to have an and. And so if we have A and B that are two sets, then the intersection of A and B, written as A upside down UB, this you're going to read as and. Notice that if you kind of draw a line here, it looks like an A. And so I use that to remind myself that that's the and. Huh? And so maybe I'll do it here. Notice that it looks kind of like an A. I'll do it like this. And so if you can remember that one, then you can remember the other one is just the other one. Usually how I memorize things if there's only two things. And so we have A and B is the set of all elements that are common to both sets A and B. So if we go ahead and we draw the same Venn diagram, just a generic A, B, allowing for some overlap, then A and B is going to be this area here, right? So just the overlap. Which brings me to the universal set. Now the universal set is always denoted by a capital U. And so you don't want to use a capital U for any other sets because it's reserved for the universal set, which is the set of all elements that could possibly happen. And so what we do is when we draw this box, this is the universal set. And so the box that I've been drawing here is showing, hey, here are all the possible elements that you could grab from. A has some of them and B has some of them, and there might be some overlap here, right? But I'm restricted to this universal set. And so the box, or I should say the rectangle, represents the universal set. Which means, and if I have, I'll do this. If I can have A and B in here. Even if there's no overlap, we usually draw the overlap anyways, right? Because it's allowed to be there, but it's allowed to be empty. And so it's just to visualize things, or if you know that there's no overlap, you can draw them not overlapping, but usually we don't know. So what's the outside of the circles? Those are all the elements that are in the universal set, but not in A or B. Which brings me to the complement of a set. Let me crop this. Hey. Come on. There. So the complement of a set A, and in this textbook, we write it as A with a bar over it. So I read it as not A. Technically, I should read as the complement of A, but I think not A is a little bit easier to wrap your head around. And so here we can think of it as not A. And so sometimes we write a superscript capital C for the complement. And what the complement is, it's the set consisting of elements in the universal set that are not in A, which is why I read it as not A. Technically, you should read it as the complement of A, but I read it as not A. So let's do a Venn diagram for the complement of A. Now, if I have A, actually, let's do a circle. Let's do A, B again. All the elements that are not in A, and this is the universal set, well, that's everything on the outside of A, but in the universal set. So ding, 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 including the elements in B that are not overlapping. So notice that I haven't shaded this overlap, right? Because that overlap is in A, right? And I want everything that's not in A. The last, I think it's the last definition. You're doing great. I know it's a lot of definitions. But is when two sets A and B are disjoint. And so usually in kind of regular language, you might have heard mutually exclusive. You can't say that because those two things are mutually exclusive, right? Is a kind of a common argument. And so what does it mean to be disjoint or mutually exclusive? Is if their intersection is an empty set, meaning that there's no elements in common. And so what we have is disjoint or mutually exclusive. We can visualize it a couple of different ways, actually. Oops. I need to draw smaller circles. A and B are disjoint. I'll add that there. Meaning that there's no overlap. And this is the universal set. It also means that a set and its complement, so the set A and the complement of A are disjoint because there are no outcomes in common, right? There's no overlap. And so what it means is that there's no overlap or elements in common. One thing that I will write here is notice if A and B are disjoint, A and B is equal to what? Must be equal to the empty set. No elements. Yes, sorry, got carried away. I'll take this time to zip this up so we can make it bigger. Good. What if you have to list all the subsets of the set of primary colors, red, yellow, blue? Let's use just R, Y, B. So you don't have to write them all out. All the subsets, what do we have to be careful of? Right, there were two kind of special notes about the subset that we made. Every set is a subset of itself. Okay? And the empty set is a subset of every set. Okay? And everything in between. Okay? And so what we can do, if we have to list all the subsets, then we could have the empty set. That's a set. Or we could have the set of just red. Right? That's a subset of those three elements. Can do the same thing for yellow. Can do the same thing for blue. I like to start with no elements, all the subsets with one element. Now let's move on to all the subsets with two elements. And so remembering that the order doesn't matter, right? So red, yellow is the same as yellow, red. So once you've listed them once, then they're the same. So let's do red, yellow. I like to be methodical. I like to go red, yellow, red, blue. And then the only one that's missing is the yellow, blue. So then red, blue, yellow, blue. And then finally, the subset where it is just itself, which I think is pretty boring, but you don't want to forget about it. Red, yellow, blue. Oh. How many subsets are there here? 1, 2, 3, 4, 5, 6, 7, 8 subsets. A little fun fact is if you have n elements, then there will always be 2 to the power of n subsets, possible subsets. So I'll do a little fun fact here. Just because if you have to list all the subsets, then, I don't know, might be nice to know. If a set has n elements, so in this case, we had 1, 2, 3 elements. It has 2 to the power of n possible subsets. For example, we have n is equal to 3, so 2 to the power of 3 is 8. And we found 8 possible subsets. That's kind of cool. It is also a way of making sure that you don't forget about the empty set or the full set itself. If you have to list all the possible subsets of a set with 4 elements, there's a lot, right? 2 to the power of 4 is what? Is it 16? Yeah, it is. but I'll confirm. 16 subsets. That's too many. Maybe an assignment question, but because I can't remember, but not on a test. Right? 3 is enough. Huh? Nice. Any questions though before we move on to the next example? If we have a set F, I'm going to just abbreviate this to A, J, R, S, S, and Y, because I don't want to write out all the names. Eichmann, Jackson, Rice, Sanders, Young. Surely this sounds like some sort of sports team. I don't know. Has to be. And B is going to be the set of Griffey, Jackson, Sanders, and Thomas. And so G, J, S, T. Luckily, they picked names that don't start with the same letters, which I checked first. Find the intersection of the sets F and B. And so the intersection is which one? The intersection is A and B. Okay. So A and B is what we want to find. Which are all the elements, oh, and I should go back up there. All the elements just in the overlapping part. Okay. And so we can list those elements as long as we're able to find just the names that overlap. Okay. So do I have an A in the second set? No, I don't. I have a J though. Okay. Do I have an R in the second set? No, I don't. But I do have an S. And do I have a Y in the second set? No, I don't. And I don't need to do it in the reverse because if it's not an A, then, or if it's not an F, I should say, sorry, then it can't be in the overlap. Okay. So then A and B is the set of J, S. That's it. If you were to draw a Venn diagram, let's see here, add a page here. Uh-oh. You know, I'm actually going to add a page here instead and just move it up. Might be easier. Whee! Than moving all those other things down. The universal set in this case would represent other players that are not in F or B, right? And so knowing what the overlap looks like, I can write F and I can write B. Now what I can do is I can write the elements in their respective areas. Right? I can have J and S in the overlap. I should have given myself more room. Maybe I still can. I know it's cheating. Hey, there. Which means that all the letters that are not in the overlap in F would go in this area. Right? And I'll use different colors just because I don't want to confuse the set name F with the letters of the elements. right? And so A, R, and Y, they're in F, but not in the overlap, right? And then in B, the set B, I have already taken into account J and S in the overlap, but I need to put G and T in the just B area. And so here, if these are players, then the universal set would be all the other players that are not in the set F or B. Nice. Now, I'm hoping, is this the same set F and B? A, J, R, S, Y, Griffey, Jackson, Sanders, Thomas. So I will make a note here. Same as above. Which means that I can cheat and I can use the same Venn diagram. You don't have to. You don't have to use a Venn diagram, right? As long as you remember that if we want to find the union, right, the union is A or B. And we have to remember what that is, right? It's all the elements in A or B or both. Okay? Notice that I'm using the A or B generically. We specifically have F and B for some reason. I don't know why, but it's going to be all the elements here. You want to be careful that you don't list the overlap twice, right? We only need to see it once. And so here, oops, F or B is the set of A, R, Y, J, S, G, T. I just read across in my Venn diagram. So if you have the Venn diagram, then that's great. That's a nice, I think, easy way to answer the question. Or if you want to just work with the sets, that's totally fine, right? What would you do? You would list all the elements of F and then all the elements of B in the same set and make sure that you exclude any overlap. Okay. And so here, notice we do not write duplicate elements twice. We only need to see them once. Once in the set. Oh, and I guess I could be specific in my, so J and S is the overlap. So I'll be specific there. All right, you only list them once. Nice. If we have a universal set, which is red, orange, yellow, green, blue, indigo, and violet, and P is the set of red, yellow, and blue, then if we want to find the complement of P, then we need to remember that the complement of P is everything that's not in P, right? And so we say that we want to find the complement of P, which it shouldn't be an angled, it's not an accent, it's just a bar. So we want to find the complement of P. The complement of P is all the elements in the universal set that are not in P. And so if I have the elements, I'll show you with the Venn diagram too, and then you can choose which one you like. Let's see here. P has red, yellow, and blue, right? So if I eliminate the elements from P that are in U, then I'm left with the complement of P, right? Everything that's not in P. So that leaves me with the set of orange, green, indigo, and violet. Or as a Venn diagram, whoops. If you prefer to visualize it, you can. We have the set P, which has red, yellow, and blue in it. And then we have the universal set outside, which has orange, green, indigo, and violet. Same method of getting there, right? And so it doesn't matter which way you use. In fact, on the test, there will only be one question where you have to use a Venn diagram, okay? And I'll point that out when it comes up, okay? But for these, you don't have to use a Venn diagram, but you might like it, right? Because maybe it makes more sense to you. Let me see here. Now I need to give myself more room. We have a universal set, red, orange, yellow, green, blue, indigo, violet, and P again is red, yellow, blue, primary colors. What if we have to find a set R so that R is not the complement of P, but R and P are disjoint? We have to remember a lot of things here from the terminology that we just introduced, right? And so what does that mean? So R can't be the complement of P, but R and P need to be disjoint, meaning no overlap, right? No elements in common. You can do it by listing the elements if you want, but I'm going to copy our Venn diagram since it's the same as, hey, I want to make it bigger. Okay. Guess not. There. There are lots of different options. Using the Venn from above. Okay. We want to find a set R so that R is not the complement of P, which means what? the complement of P is everything outside of P, right? And so we're not allowed to say, okay, fine. We can't do that, right? But I can do this, right? Or this, or this, or this. As long as I'm not taking all four at the same time, right? Then I've found a set that satisfies this criteria. Okay? And so as long as we don't use the complement of P, which is OGIV, is equal to R. Right? We can use any combination. Oops, this is equal to R. We can use any combination of those four elements as long as we don't use all four. We can use any combination of those four elements as long as we don't use all four. I'll use the number 4, even though I probably shouldn't. So for example, R can be the set of OGI, or it can be the set of GV, or it could be the set of O. It could even be the empty set, but I don't want to lead you down that road. It's too tempting. How about the empty set? It's always an answer if you're looking for subsets. Oh. And maybe I should change this to G because it looks like a 0. There. Right, so you could have 3, you could have 2 elements, or just 1, as long as you're not using all 4, etc. Lots of different options. So that's kind of a fun one. Same universal set, same P. So red, orange, yellow, green, blue, indigo, and violet for our universal set. P is the primary colors, red, yellow, and blue. And Q is the set of red, green. R is going to be the set of orange, green, and indigo. And we want to find this set. Now this is going to make one set. Huh? But you want to be really, really careful. We've seen this before, right? In logic, where, hey, I forgot for a second that we did logic, right? So you've seen the or and the and, but they were just these instead of yous, right? And so I forget. Usually when I teach sets, they haven't seen logic yet. So you guys are lucky. Oh. So they'll feel extra familiar. What we want to do, just like in logic, you want to build this out nice and slow, right? And so P or Q, but then not that, right? So then the complement of that and the complement of R, right? Or not R. And so here, I'll say we need to build this out. So what I'm gonna do first is I'm going to list the elements of P or Q. Then I'm going to negate it, right? Or take the complement, which is basically negating it. And so P or Q, red, yellow, blue, or red, green. Now the red, I don't list it twice, and so P or Q is going to be red, yellow, blue, green. Now the complement of that is my next step. So P or Q, the complement of that is going to be everything in the universal set that's not in P or Q. Which is going to be not red. I am allowed to have orange, not yellow, not green, not blue. I am allowed to have indigo and violet. I'm gonna count the elements of my set just in case I forgot something. I have 1, 2, 3, 4, 1, 2, 3, so I have 7 total. And 1, 2, 3, 4, 5, 6, 7 in the universal set, right? Because the complement has to be the opposite of the original set. Right? So now we've dealt with this set. Now we want to find the intersection of the set that we just found and not R. Now I would recommend finding not R first. I'll use purple. So not R is all the elements in U that are not in R. R has orange, green, and indigo. And let's see here, I'll just orange, green, and indigo. Which means not R has red, yellow, blue, and violet. I'll erase these. So now I want to find this set and this set, right? So the overlap of these two sets. P or Q, not, and R not. The overlap. Is there an O in here? No, there isn't. Is there an I in here? No, there isn't, but there is a V. All right. And of course, if I'm looking for the overlap and I've run out of elements to check in the first set, then they can't be in the overlap because they're not in the first set. Right? And so we're just left with one single element, V. It's harder to do in a Venn diagram. You can. Should we try it? No. Usually so keen. You can try it on your own, but usually it involves, just like we had to break it down into multiple steps, right? Then you would have to kind of do a couple of iterations, right? And kind of reshade areas that you want. And so in this case, I think just listing the elements might be easier, but you can try it with a Venn diagram if you want. It's not until now that we introduce the Venn diagram but we've been using it already, so I'll just kind of breeze through it. A Venn diagram, represents a set as the interior of a circle, right? So we visualize sets as circles. Often two or more circles. I'll show you what a three set Venn diagram looks like here. Copy, crop, come on. And paste and crop this up. And then move these down. So a two set Venn diagram versus a three set Venn diagram. We stop at three. There are four set Venn diagrams, but three is plenty. So a two set Venn diagram is going to look like this. So you've got your universal set and you've got your generic sets A and B. That's what we've been working with so far. A three set Venn diagram. Now you need three circles. Usually how we draw them is like this. So now we can have A, B, or C as our sets. Notice that we have to have all the potential overlaps, right? And so here, what's this overlap? This overlap is the overlap of A and B and C. Right? And still the universal set outside. So it's just good to know what a two set Venn diagram and a three set Venn diagram looks like. And I think I've seen a five set Venn diagram before, but it's crazy. They kind of have to go like outside and yeah, they're weird. Can look them up. So, suppose a survey of car enthusiasts showed that over a certain time period, 30 drove cars with automatic transmission and 20 drove cars with a standard transmission and 12 drove cars of both types. So the both would be the overlap. If everyone in the survey drove cars with one of these transmissions, how many people participated in the survey? And so I think that the easiest way to solve this is with a Venn diagram. But now instead of listing each element, we're going to list the number of elements, because that's all we're given. And let me move this down. So we can have automatic transmissions or standard transmissions and the universal set. Here, note, when we are not given the individual elements, we usually write the number of elements in each area. When we're not given the individual elements of each set, we write the number of elements in each area. instead. You'll always want to, and let's see if I can maybe move this. Make this a little bit bigger. There, make my overlap a little bit bigger. For these problems, what you want to do is you want to write down the elements in the overlap first. So always start in the area with most overlap. I say most overlap because here, if you only have two sets, then of course there's only one overlapping region. But if you have three sets, which we'll soon have, then you'll want to start here with all three overlapping and then move out into the other overlaps. I'll show you what I mean. So we've got automatic transmissions, standard transmissions, and 12 drove cars of both types, which puts 12 in the center. So you want to start there. Because now 12 are already accounted for. And so now what you want to do is, yes, the A circle should have a total of 30, right? But what we do is we write just how many are in each region. Okay? So you don't want to write 30 here because you've already taken 12 into account, right? Which means that I have 18 here. 30 minus 12 for both, which is 18, yeah? Had to confirm. Nice. And so that's where this 18 came from. And then 20 drove cars with standard transmissions. So that means that I have 20 minus 12, which is 8 here. In just the standard. Right? And so how you read this as is 18 drove only automatics, 8 drove only standards, and 12 drove both. And if everyone in the survey drove cars with one of these transmissions, then how many are on the outside? 0. Right? There are no elements outside of these. So now, how many participated? What you want to do, oops, is add a page first. Give me some room. You want to add up all the individual areas. Add up all the individual areas. $18 plus 12 plus 8 plus 0. Bless you. Don't think about it. It's the worst. Putting me at 28. 38? 38, I think. Yeah. Let me, 18 plus 12 plus 8 is 38. Nice try, Emily. Nice. Notice we can't use just 30 plus 20, right? Because then we're counting the overlap twice. Once is good, but twice is bad. Right? And so notice we can't use 30 plus 20, which is 50, since that would count the overlap twice. See, what formulas do I have for sets? Not much, huh? Just permutations and combinations. That's next day. So all of these formulas you have to memorize. There aren't really formulas, they're just concepts, right? Makes sense that you'd have to memorize them, I guess. A survey of 100 people in California, which tells me that the total areas all have to add to 100. Indicates that 60 people have visited Disneyland, 15 have visited Knott's Berry Farm, and 6 have visited both. So I've got a set for Disneyland, a set for Knott's Berry Farm, and those who have visited both. And then, of course, there are some number that have been to neither, right? And so we want to find how many people have visited neither place, which is essentially the complement of Disneyland or Knott's Berry Farm. But we can solve with a Venn diagram, I think, is the easiest thing in this case. So we've got the universal set, which is the 100 people in California. And we've got those who have been to Disneyland. I feel like this is the second class in a row where I mentioned Disneyland. That's really funny. Wasn't I blabbing about Disneyland last day? No, it's very fun. I'll just use K. And some number have visited both. So again, what you want to do is you always want to start in the center, right? And so 6 have visited both. Start there. And I'll make a note here, start here. And then you want to make sure that you take away these 6, right, from the overall Disneyland circle, because the overall circle includes those 6. So 60 minus 6 is 54. And 15 have visited. But that means the total K circle has to be 15. Taking away the 6 that I've already represented, I get 15 minus 6, should be 9. Now, the universal set is all the 100 that haven't been accounted for yet. So 100 minus 54 minus 6 minus 9. A 100 minus 54 minus 6 minus 9 puts me at 31. So 31 have been to neither. Therefore, 31 have been to neither park. I didn't even know Knott's Berry Farm existed until like just a couple of years ago, I think. What? But I think, isn't it more roller coasters if it even exists still? I feel like it's more just roller coasters. Whereas Disneyland is like everything, I guess. As we established last week, it's been a while since I've been there. I was there in 1995. I should dig up, I'm pretty sure I still have, you know, those like big ridiculous pins that you'd bring back.
Oh, yes.
Pretty sure I have one that says 1995. I should dust that off.
Take it with you next time you go.
Yeah. Mm-hmm. It's somewhere in the garage. Okay. First of all, any questions about that one? This, oh, that's what I wanted to write. I knew I had something. Or Disneyland or K, the complement of that has 31 elements. Right, you can confirm that this 31 is just the complement of D or K. I do want to make a note that when we're counting the elements, it's called the cardinality. And so this is just a side note. The cardinality of a set is the number of elements in that set. The cardinality of a set is the number of elements in a set. Denoted by, denoted by these vertical bars. The cardinality of, and maybe I'll use D. The cardinality of D was 60, right? All the elements of D, which includes just D as well as the overlap, right? And so the cardinality of D is 60. Or sometimes we write N of D is 60. That's not going to come up because they didn't introduce it in the textbook, and so you don't need to know it, but it might just be nice if you see cardinality somewhere, right? It's just the number of elements in the set. So therefore, the cardinality of D or K, what we found, is 31. Oh, sorry, the complement. There. maybe I'll say, oops. Therefore, we found that the cardinality of D or K naught is 31. Nice. So those vertical bars, you might remember the absolute value, right? Where you just drop the negative, right? Now for sets, they mean something different. It's just the number of elements in the set. How am I doing for time? 7:23. Feeling a lot like 8:23. Okay, we're doing good. Only because to try to sneak in 7.4, I have to kind of do 2 sections today, or at least start the second section. I know, rude. Rude, rude, rude. But it'll give us more time to review later, so that's nice. A survey of 100 exercise conscious people resulted in the following information. 50 of them jog, 30 of them swim, and 35 cycle. So now all of a sudden I'm noticing 3 sets. And so I have 3 sets. Jog, swim, cycle. Luckily, we know what the 3-set Venn diagram is. And so for 3 sets, we always use a Venn diagram. A Venn diagram to solve. And on the test, it'll even say, draw the Venn diagram representing all the areas and all the sets, right? And so it'll be laid out just like this. And part A will be draw the Venn diagram representing and labeling all the appropriate areas, not to lead you on too much, right? And then use the Venn diagram to answer some questions. Yeah? All the hard work is drawing the Venn diagram, and then answering the questions is usually not that bad, right? Because you've already done all the work. Yeah? And so for the 3 sets, it'll say explicitly, so like I promised, right? You don't have to use a Venn diagram, but if you like using a Venn diagram and it makes sense to you, then you can use it for the other set questions. But for a 3-set Venn or for a 3-set question like this, right, jog, swim, cycle, for example, then you'll have to use it or draw a Venn diagram, right? And then it'll be easy to use it to answer the questions. 14, jog and swim. Notice that that's the overlap of the jogging and the swimming. Okay? 7, swim and cycle, so that's the overlap of swim and cycle, and 9, jog and cycle. And 3 people take part in all 3 activities. So first things first, and maybe I should use a different color here. Always start here at the innermost overlap. And you know what? I'm just going to put this on its own page here. It's a big question, so let's start out by drawing a Venn diagram. A 3-circle Venn diagram. we've got the joggers, the swimmers, and the cyclists. Okay. So when we're drawing these, right, you want to start at the very, very innermost part and then work your way out, remembering that you've already written down the overlap. Right? And so what this is going to look like is we have 3 here in the very, very center. Right? Now, we're told, so now working your way up. So now you can kind of work your way up the ladder. 9, jog and cycle. Now jog and cycle, let's see if I can find. Jog and cycle is this whole bit. That kind of almond shape. But you've already written down 3 of those, right? And so you want to make sure that you don't write 9 because this whole thing has to add to 9, right? Making this area 6. Doing the same thing for the next part. 7, swim and cycle, making sure that you swim and cycle. And so the overlap here makes this area 4. Now, probably have the hang of it. 14, jog and swim. And so jog and swim, well, that's here, but I already have 3 of them, which means that 11, running out of colors here, 11 only jog or swim and not all 3. Okay, so we've got all the overlaps. Now we need to carefully tackle the 50 jog, 30 swim, and 35 cycle, remembering that you already wrote down some of those elements, right? And so the total circle for jogging has to add to 50, right? And so this whole circle, let's see here. What color can I use? I don't know. I'm out of colors. This whole circle has to add to 50. 50. But 6 plus 3 plus 11 are already accounted for. So really what you can do is you can do 50 minus 6 minus 3 minus 11, putting me at 30 in this area. Doing the same thing for the swim has to add to 30. So I need to chip away 11, 3, and 4. So 30 minus 11 minus 3 minus 4 puts me at 12. And then finally for the cyclists, the total has to be 35. But I've already got 6, 3, and 4. So 35 minus 6 minus 3 minus 4 puts me at 22. And finally, the universal set. Some of these people don't do any of it, right? That's allowed. We're told that we have 100 exercise conscious people. They can do other exercise, not jogging, swimming, or cycling. can't think of anything right now, but there are no other sports. Skiing, I don't know. Yeah, sure, I guess there are other options, I'm just blanking. So here, the universal set must be 100 minus all of these other areas, just as we did before, right? We've already accounted all of these other areas. And so there's a couple of different ways that you can do it, but I like to use the same method always, where I just subtract the ones I don't want, right? And so this is 100 minus 30 minus 11. And try to do it kind of methodically, minus 12, minus 6, minus 3, minus 4, minus 22. Making sure that you kind of caught all the areas. 30, 11, 12, 6, 3, 4, 22. Now let's see here. One. It's 12. Thanks. Thank you. Which makes that outside area 12. Huh? So on the test, you'll have a question that'll look just like this. And it'll be a 3-set Venn diagram. And then, so the first part will say, draw the Venn diagram, labeling all the areas, right? Now we can answer the question. And of course, if you've drawn the Venn diagram in the same question, you're allowed to use it. And so that means that you don't have to show any work, right? Because you've already done the work making the Venn diagram. How many jog but do not swim or cycle? $30. So they're not allowed to swim and they're not allowed to cycle, leaving me with 30, but they have to jog. And so I'll make a note here. If you have drawn the Venn diagram, you do not need to show work. You've already done all that work, right? Now you're just reading it. Oh. How many take part in only one of the activities?
60.
You guys are so fast. I haven't even said it yet. 30 plus 12 plus 22, right? I will show this work. 30 plus 12 plus 22. But if you just said 64, that's fine. Finally. How many do not take part in any of these activities? Well, we already did that work. That's all these guys, 12 of them. Cross-country skiers, maybe. I don't know. Nice. Any questions about those ones? They're pretty fun once you get the hang of them. As long as you remember to start in the center and move your way out. We are going to start this section. And then we can take it easy later. How about that? We're here, we may as well do it. Oh, let me check the time though. Okay. I've got just a smidge of time. I just want to introduce the next section and then we'll pick up here next day. So like I said, when we talked about counting, really what we're doing is not just 1, 2, 3, 4, 5, although kind of in theory we are. No. But what we're talking about is if we have a problem like this. So if a woman has 2 blouses and 3 skirts, how many different outfits consisting of a blouse and a skirt can she wear? Yeah. And so one of the ways that we can solve this is with a tree diagram, where she's first going to pick a blouse and then she's going to pick a skirt. And so a tree diagram is going to look like this. First, she's going to pick a blouse, and then she's going to pick a skirt. She had 2 blouses, so blouse 1 and blouse 2, and 3 skirts. Skirt 1, skirt 2, and skirt 3. Notice that I put skirt 1, skirt 2, skirt 3 at the bottom of blouse 1, but of course, she has the same skirt options if she chose blouse 2. And so what we do is we represent that with the same scenario, skirt 1, skirt 2, skirt 3. So now, at the bottom of each branch, or at the end of each branch, we have the possible combinations, right? And so here we have our outfits. Let me just move this over just a bit. So our outfits, I can have blouse 1, skirt 1, blouse 1, skirt 2, blouse 1, skirt 3, or I can have blouse 2, skirt 1, skirt 1, blouse 2, skirt 2, and blouse 2, skirt 3. How many different outfits can she wear? I'm counting 1, 2, 3, 4, 5, 6 different outfits. 6 different outfits. I want to introduce the multiplication axiom right away because we don't actually need to use a tree. I think a tree is hard. So when I give it to you, it probably makes sense. You look at it and say, great, yeah, that makes sense. She chooses a blouse, she chooses a skirt. You could have done the same thing. She chooses a skirt with 3 branches at the top. And then at the end of each of those branches, you have the 2 blouses. You would end up with the same number of different outfits, right? Another way to solve this, is to use what I call slots. They don't really have an official term. Pending, trademark pending, I guess, but just slots. Now how and I was taught with slots, but they're not really official, is we have a slot for the blouse and a slot for the skirt. Remembering that we're going to say and in between, and is going to be multiplication. And so when we say and, it results in multiplication. What you want to do is write down how many options do you have for the blouse. Okay. We've got 2 options for the blouse. And how many options for the skirt? 3 options. So the number of options for the blouse and the number of options for the skirt, which gets me to 6 total options. So when I say we'll use the slots, because these slots, we're going to be able to use them for a lot of different scenarios, right? And so then I make a slot for my first thing that I want to fill, the blouse in this example, and then I make a slot for the second thing that I want to fill. And just to seal the deal, let's do this next example. If a woman has 2 blouses, 3 skirts, and 2 pumps, because it's the 80s, I guess. Although they must be coming back at some point, right? Pumps, I don't know. My mom wore pumps a lot. How many different outfits consisting of a blouse, a skirt, and a pair of pumps can she wear? This is the same scenario, right? And so now we're just adding on. So I have my blouse. And I have a skirt, and I have some pumps, which are just shoes. They're like a low heel pumps. Remembering that I want to multiply across because I'm saying and a skirt and pumps. Well, so I have 2 blouses, 3 skirts, 2 pumps. Now I have 2 times 3 times 2, putting me at 12 outfits. We'll use a tree diagram for harder questions. So this one, I don't actually see why they introduce it here. We will use tree diagrams later, but I think the slots are easier for this, right? So I'll, just like with the Venn diagram, I'll highlight when you actually need to do the tree, right? Otherwise, slots work most of the time. Right? Okay, and we can do it. We're here. The slots, because I already introduced them, are really the multiplication axiom. And so the multiplication axiom is really when we're using our slots. If a task can be done m ways and a second task can be done in n ways, then the operation involving the first task followed by the second task, which you could read as the first task and then the second task, can be performed in m times n ways. So really what that means is task 1 and task 2. I have m, n. So I have m times n ways total. License plates are a common use of the slots, right? And so a truck license plate consists of a letter followed by 4 digits. how many such license plates are possible? Huh? And so one thing or a couple of things, just note there are 26 letters. And there are 10 digits, okay, because 0 is a digit, right? And so there are 10 digits. 0, 1, 2, 3, all the way up to 9. Yeah? So you want to make sure that you remember 0, right, as an option. So in terms of our license plate, if we have a letter followed by 4 digits, 1, 2, 3, 4, it would look like this. Right? How many options do I have for the letters? Well, I have 26 letters. And there are no restrictions on the digits, right? I could have 0, 0, 0, 0. There's nothing that says I can't, right? And so then for each of these, I have 10 digits. And multiplying through here, it's going to be some very big number. 26 times 10 times 10 times 10 times 10. Well, surprise, surprise. But I can't keep track of all those zeros. 1, 2, 3, 4. Yeah. Which means that there are 260,000 possible plates. In BC, I think a truck license plate, I know a truck license plate has 2 letters followed by 4 digits. Right? And so then you would have 26 times this many plates to choose from. It's a lot of trucks. That's just trucks. What I want you to do, because I will release you now, is try these because you've seen the slots. And so try these and we'll use them for a review on Wednesday. And with that, I release you. Great job. I'll stop this recording.
Let's go.